All right, so now we're going to apply the things that we have been learning, so adding, subtracting, and multiplying polynomials to applications. Let's get to it. First, a basketball court has dimensions in feet of 8x plus 4 by 4x plus 6. What is the area of the basketball court? So, first we need to think about what is the shape of a basketball court. A basketball court is a rectangle. Then we need to recall, how do we find the area of a rectangle? Great question. Area of a rectangle. Whoops. We can think of as length times width, base times height, right? And I'm going to use a little subscript here for C, so area of the court, only because I know already part B is going to have an area of a stage. And I don't want to just call everything A, because that could potentially get confusing. So area of the court is length times width, where one of these is the length, and the other one is the width. It doesn't matter which we call length and which we call width. We just need to do the multiplication. So I want you to do that. Pause the video, unpause when you are ready to check the area. All right, so hopefully you end up with area of the court is 32x squared plus 64x plus 24. How do I get that? Again, area of the court is length times width. I called the 8x plus 4 the length, the 4x plus 6 the width. I did my distributing, carefully combine like terms, and I got my area. Next, a stage has dimensions in feet, 2x plus 5 by x minus 1. What is the area of the stage? Now, it doesn't specifically say this here. We are going to assume the stage is a rectangle since we are only given 2 dimensions. So, I want you to go ahead and find the area of the stage. Pause the video. Unpause when you're ready to check. All right, so hopefully you got the area of the stage, and again here I'm just calling it A sub S so that I'm not confusing with the area of the court, is 2x squared plus 3x minus 5. I got that by taking the one dimension, 2x plus 5, and multiplying it by the other dimension, x minus 1. I distributed it carefully, combined like terms, and I got my area, 2x squared plus 3x minus 5. Next, so here's the application part, right? Well, I guess this has all been the application part, but if the stage needs to be set up on the basketball court for a concert, what is the area of the remaining floor space? So I want you to try to do this on your own, but think about this is the area of the total floor space of the basketball court. This is the area of the stage. We're trying to figure out if the stage gets put on the court, what is the area of the remaining space? How do I do that? What is the relationship between these two? So I want you to try this on your own. If you get stuck or you're confused, just unpause and hear the explanation. But try it on your own first if you can. Unpause when you are ready to check, or like I said, if you get stuck or confused. All right, so here we should get the remaining area is 30x squared plus 61x plus 29. But how do we get that? We get that by subtracting the area of the stage from the area of the court. Or I do area of the court minus area of the stage. So that's the work you can see set up here. This is the area of the court minus the area of the stage. So the only thing I have to do is be careful, distribute the negative. And now it just becomes a matter of combining like terms. And that's how I got 30x squared plus 61x plus 29. Questions on that? All right. Well, and again, I'd just like to reiterate, that's why it's important for us to understand context, right? In this case, putting the stage on the court. So I'm going to subtract the stage from the court, and that will be what is left over. Next one, here, I want you to find the volume of the box. Again, we have to recall, well, how do we find volume? Hopefully we remember volume of a box is length times width times height. So go ahead and pause the video, find the volume, unpause when you're ready to check. Okay, so hopefully we came up with the volume is 42x to the third plus 49x squared minus 35x. How do we do that? Well, we already knew length times width times height is volume, so 2x minus 1 times 3x plus 5 times 7x. I chose to distribute the 2x minus 1 and the 3x plus 5 first. So remember the 7x just kind of hangs out. And I get 6x squared plus 10x minus 3x minus 5, combined like terms, so 6x squared plus 7x minus 5. And then now I distribute each term to the 7x. That's how I end up with 42x to the third plus 49x squared minus 35x. Okay, last one we're going to look at is another model. The estimated number v in thousands, so it's important that we recognize in thousands. That's going to be big. Electric vehicles in use in the United States can be modeled by this given function here, where t represents the year with t equals 1 corresponding to 2001. Use a graphing calculator to graph the function on the interval 1 to 10. Describe the behavior of the graph. Okay, so let's go to our graphing calculator. So I'm going to go to my graphing calculator. I'm going to do y equals, and now I need the function, so 0.151 t to the third, 0.151. Remember on the calculator we just use x no matter what the variable is in the equation. So I'm going to do x to the third. Then it was minus 3.28 t squared. So minus 3.28 x squared plus 23.75 t minus 2.04 plus 23.75 x minus 2.04. Just make sure I have that correct. Okay, great. Now, if I just hit graph, this is what I see. That's not terribly helpful. So what did it say? It wanted me to graph it from 1 to 10, right? Because it said from 1 to 10. Also, so I'm going to adjust my window. If I go to my table, I want to look and see, okay, well, when x is 1, the y values are 18. And when x is 10, the y value is 58. So I'm going to adjust my window. I know my x min, I want 1, and my x max, I want 10, because the problem told me that. For my y min, I'm just going to put 0. And my y max, I'm going to put 60. And the reason why I'm going to put 60 is because, remember, at 10, it was 58, or 58.46. So I want to be just a little bit above that so that I can actually see what is happening. Also keep in mind, what does y represent? And remember, y is the number of vehicles in thousands, okay? So putting y min at 0 is fine because we can't sell a negative amount of, or have a negative amount of vehicles. Okay, so now if I hit graph, this is what I see. Okay, so how would we describe that? So let's go back to the first question, describe the behavior of the graph in this interval. Well, as we go from left to right, is the graph going up or is it going down? Hopefully we see it's going up. So I would say that this is increasing. Next question, what is the average rate of change? So average rate of change, using techniques that we know so far in this class, this is just another way of saying slope. So I'm going to find values, and I know I have a point that is 1 comma. So if I can look at my calculator again, and I'm going to go to my table. 1 comma 18.581. And then I have another point that is going to be 10 comma, and I know it was 58 point something. Let's go back to the calculator. 58.46. So 0.46. And so then remember, slope is, I'm going to use m, so y2 minus y1 over x2 minus x1. So then I plug my numbers in, I do my calculation, and I get 4.431. So the average rate of change is that the electric vehicles increased by approximately 4,500 vehicles every year from 2001 to 2010. So that's what this is telling me, because remember, this represents thousands, and it's pretty close to 4.5. So the average rate of change is 4.431, but what that's telling me is an average increase of 4,500 vehicles a year. And then the last question is just kind of, use some common sense. So do you think this model can be used for years before 2001 or after 2010? Well, let's look at before 2001. So if I look when x is 0, I have negative vehicles. So that doesn't make sense, right? I can't sell a negative amount of vehicles. So before 2001, absolutely not. After 2010, maybe, at this point, it's kind of like, well, we know what's happened, right, with electric vehicles. And we have an idea of how they've grown, right? But maybe this model is not exactly accurate. We would have to actually look at those numbers. However, in general, remember, we don't want to use the model after that, after this date, because that's extrapolation. And remember, this is something we talked about in our linear modeling unit, was that if the model is only good or designed to be used between 2001 and 2010, then using it beyond that is not a great idea. There are times where we have to do that, and maybe it's a good model, but there's always a risk involved. Okay, so just to kind of sum this up, remember that we need to know our basic rules of geometry, so like areas and volumes, maybe surface area, to then combine with our algebra when we are using polynomials with modeling. We also need to think a little bit about context, right? On the basketball court and stage problem, understanding that we are going to do subtraction because we're trying to find the area left over.